Good day, we'll discuss basic calculus based on the teaching guide for senior high school. So chapter 1 is on limits and continuity. The limit of a function. So over 1,000 years ago, Archimedes was able to approximate the area of a circle using the area of a regular polygon with n sides inscribed in a circle. So we have this. When we say regular polygon, it means that the polygon has the same side length and angles. So equiangular and equilateral. So here we have a square, so with 4 sides. So next we have a pentagon inside, a regular pentagon inside the circle. Next we have a regular hexagon inside the circle. Now imagine what happens to the area of the inscribed polygon. Okay, imagine what happens to the area of the inscribed polygon with n sides as n increases without ending. So meaning as n maybe approaches infinity, as n increases. So of course, maybe one of you may imagine that the polygon, the figure of the polygon will somehow look like the area of a circle. Okay, so the polygon will somehow look like the area of will look like the shape of a circle. So that is why the area of the inscribed polygon becomes the area of the circle. So this is how Archimedes approximated the area of a circle. So that's the approximation. So Archimedes studied the behavior of this polygon as n increases. Okay, study the polygon, the regular polygon as n increases. So the same here with functions or limits of a functions. We will consider functions of a single variable and study the behavior of the function as its variable approaches a particular value. So same with our illustration, the polygon approaches a circular shape. So here, in general, we will study a function or a single variable function and study the behavior of that function as its variable approaches. Take note, approaches a particular value. So it means that a variable can only take values very, very close to the constant, okay, to the constant, but it cannot equal itself or the constant itself. Okay, take note. Okay, we will only study the behavior as it approaches. Okay, so say for example, if we have a constant here, okay, so this is the point. So we will study the behavior of the function as the function approaches this one, or as the variable approaches this. So what happens to the function? Okay, so however, the limit will be able to describe clearly what is happening to the function near the constant. Okay, take note, the limit will be able to describe, since we are studying the behavior of the function as the variable approaches the constant. So the limit will be able to describe what happens there. So limits are the backbone of calculus, and calculus is called the mathematics of change. The study of limits is necessary in studying change in great detail. The evaluation of a particular limit is what underlies the formulation of the derivative and the integral of the function. Of course, before going to discuss derivative and integral, we'll study first the backbone, which is the limits. So consider a function of a single variable x. Consider a constant c, which is the variable which the variable x will approach. So meaning x will approach c. Okay, so x will approach c. So c, take note of this, c may or may not be in the domain of f. So it is not necessary that c is in the domain of f. So it can be or it cannot be in the domain of f. So it may or may not be. The limit, to be denoted by L, is the unique real value that f of x will approach as x approaches c. Okay, I repeat, the limit to be denoted by L is the unique real value that f of x, or the function, will approach as x approaches c. So in symbols, we write this process as limit of f of x as x approaches c. So in general, this is read as the limit of f of x as x approaches c. So we have an arrow here, x arrow c. X approaches c is L. So we read this one as the limit of f of x as x approaches c is L. Now let's study these limits by studying the table of values. So let us consider first this. Limit of 1 plus 3x as x approaches 2. So here, based on our notation, our f of x is the 1 plus 3x. And our c here is 2. Okay, our constant here is 2. Okay, so x approaches c. So x will approach 2. So to evaluate the given limit, we will make use of a table to help us keep track of the effect, since we're studying the behavior. So we have this to keep track of the effect that the approach of x toward 2 will have on f of x. So let's have this. So on the number line, x may approach 2 in 2 ways. Take note how the number line, meaning we have the, if we look at the x-axis, okay, we have through values on its left and through values on its right. Say for example, with this illustration, if we have this graph, so if this is our c or our 2, we have two possibilities. From the left, so this side is left, so from the left, as x approaches from the left, and this one is as x approaches from the right. Okay, so we have two possible values, approach on 2. It's from the left and from the right. Okay, so remember that the values to be chosen should be close to 2. Okay, so say for example, we have this. Take note, f of x is given by 1 plus 3x. Okay, 1 plus 3x. So if x is equal to 1, so if x is equal to 1, we have 1 plus 3 times 1. So we have 1 plus 3, so we have 4. That's why we have 4 here. Next, let's have 1.4. So if it's 1.4, 1 plus 3 times 1.4 is equal to 1 plus, what is this equal to? 4.2. So this is equal to 5.2. Okay, and so on. Okay, so meaning in this case, you will just do the evaluation of the function. So you just substitute the value of x here. So that is evaluation of functions based on the general mathematics on your grade 11 or in your grade 11. So just substitute and take note again that our x must be closer to 2. So look at this, 1, 1.4, 1.7, 1.9, 1. So on. And of course, you're allowed to use your calculator. So if you look at this from 1.9 up to 1.9999, so we have this 6.9997. Now, this is from the left of 2. Remember, this is from the left of 2. So if we have a number line and this is 2, of course, this 1, 1.4, 1.7, and 1.99 are all from the left side. So this is as x approaches 2 from the left. Okay, from the left. Now this one is from the right. So 3, 2.5, 2.2, 2.1, 2.3, and 2.001. So these are the values here, and this is from the right. Okay, so we have these values. So just substitute 3 here from the given function. So 1 plus 3x. So you will arrive with these values. Okay, now, so what have you noticed? Okay, as x approaches 2, as x gets nearer to 2, our f of x gets nearer to what? It gets nearer to 7. Now, let's look at this from the other side, from the right. As x approaches 2 from the right, so again, it gets also closer to 7, right? So it gets closer to 7. So as the values of x gets closer and closer to 2, the values of f of x get closer and closer to 7. So this behavior can be shown no matter what set of values or what direction is taken in approaching 2. So meaning you may continue adding more numbers here, not exactly 2, but smaller or number nearer to 2. Other numbers nearer to 2 if you may add, and the result is still this. The f of x approaches 7. So as x approaches 2, the f of x approaches 7. So therefore, the limit of 1 plus 3x as x approaches 2 is equal to 7. Okay? Take note of the behavior. That's the behavior. As x gets closer to 2, our f of x gets closer to 7. Okay, now let's have other examples. So let's investigate this. The limit of x squared plus 1 as x approaches negative 1. Okay, so take note, this is our f of x, and this is our c, the negative 1. So let's study again from the left and from the right. So we have this table. This is from the left. So take note, this is approaches negative 1 from the left. Okay, so what have you observed? The value, of course, approaches 2. Okay, it approaches 2. Now let's have the value from the right of negative 1. So by substitution, so you will arrive with this value using this x squared plus 1 as your f of x. So by substitution, we have this. And as x approaches negative 1 from the right, again, it approaches 2. Okay, it approaches 2. So the table show that as x approaches negative 1, f of x approaches 2. So in symbols, we have this. Limit of x squared plus 1 as x approaches negative 1 is 2. Now another example, the limit of the absolute value of x as x approaches 0. So this is from the left and this is from the right. So take note, this is the values of x from the left, so it's negative. And this is from the right. So take note what happens. As the number gets smaller and smaller, this one smaller and smaller, and for this one bigger and bigger, nearer to 0, then of course, by observation, this approaches 0 as well as this approaches 0. Hence, the limit of this one is 0. Now, example 3. Limit of x squared minus 5x plus 4 all over x minus 1 as x approaches to 1. Take note that by our note last time, the c may or may not be in the domain. Take note, by just looking at this, x equals 1 is not in the domain because x minus 1 is 0, right? When x is equal to 1, this fraction here, or this rational fraction or rational function here, will become undefined. So basically, 1 is not part of the domain. Okay, but of course, this is not a problem because as what we note in the previous slide, the C may or may not be in the domain. So C can also be outside the domain. Okay, so take note of that. So in evaluating limit, remember that we only need to go very close to 1. Take note of this, very close to 1 and not equal to 1 itself. Okay, so take note of that. So we now approach 1 from the left. This is from the right. Okay, so this is from the right. So we have 1.5, 1.17, and if you notice what happens, so it approaches negative 3. Okay, so it approached from the right because 1.5, 1.17, 1.003, 1.0001 are from the right of 1. Okay, take note, if we have 1 here, these values, these x's are here. So the x approaches from the right. And this is from the left. Okay, so as x approaches from the left, so meaning if this is 1, these values, these x's are here. Okay, from the left. It approaches 1 from the left. So based on this, the same thing, this will approach negative 3. Okay, so the table show that as x approaches 1, f of x approaches negative 3. So in symbols, we have this. Okay, so again, our C may or may not be in the domain. Okay, because we will only study the behavior of x as x approaches a given value. Now, let's investigate through a table of values. We have this. This is a what? A piecewise function. So, of course, this is a piecewise function. So, this looks a bit different, but the logic and the procedure are exactly the same. So, we will still approach the constant 4. Take note as x approaches 4. It's from the left and from the right. But note that we should evaluate the appropriate corresponding functional expression. That is, say for example, we have 4. So when we say approaches from the left, this one, meaning this is less than, the values here are less than 4, right? The values here are less than 4. So meaning our f of x here, we will use x plus 1. Okay? Now for the right side, as x approaches from the right, so we will use this. X squared minus 4 plus 3. Okay, so let's study this. So this is as x approaches 4 from the left. So we have 3.7, 3.8, 3.99, and so on. So these are the values from the left of 4. And take note, it approaches 5 by observation. On the other hand, when x approaches 4 from the right, so this is from the right of 4, the values taken should be substituted in this one, of course. No? So since, as what I've told you, if it's greater than 4, since it's from the right, so you will use x minus 4. We have the square of x minus 4 plus 3. And this one, by the way, since it's less than 4, so this is less than 4, so it uses the x plus 1. Okay, so that is why we have 3.7 plus 1, 4.7, 3.85 plus 1, 4.85, and so on. And since, on the other hand, from the right side, this one, this is from the right of x, or from the right of 4, then we will use the square of x minus 4, and then plus 3. Okay, so take note, we have here 3. Now observe that this time, the values f of x approaches are not equal. So here, as x approaches 4 from the left, it approaches 5. F of x approaches 5. But on the other hand, as x approaches 4 from the right, f of x approaches 3. Okay, so in such case, we say that the limit of a given value or function, so the limit of a given function does not exist, or D and E. So in symbols, we have this. Take note, we are not using the equal symbol. So just write limit of f of x as x approaches 4, then write the capitals D and E, meaning does not exist. Okay, so in short, if the values of your limits, or if the value of your f of x as x approaches constant, a specific constant, from the left and from the right are not equal, then of course the limit does not exist. Okay, so take note, do not say that the limit f of x equals x approaches 4 equals D and E, and do not write this one because D and E is not a value. Okay, so just write it like this, does not exist. So have you noticed a pattern in the way we have been investigating a limit? So what have you observed? Now, from based on the tables, we always what? Use the table, a table from the left and from the right. So as x approaches a value c from the left, and as x approaches value c from the right. Okay, this direction may be specified in the notation. So by adding certain symbols. So if x approaches c from the left or through the values less than c, then we write these symbols. We have the minus. Okay, this minus symbol means left. The x are on the left of c. So meaning, if we have c here, and if it's minus, meaning if c minus, meaning the x is from the left of c. Okay, and if it's plus, this one c plus, then of course the x's are from the right of c. Okay, so I hope it's clear. If it's minus, it's from the left of c, and if it's plus, then it's from the right of c. So furthermore, we say that the limit of f of x as x approaches c is L if and only if these two limits from the left and from the right are the same, or they have the same limits. Okay, so that is why, based on our previous examples, okay, from examples 1 to 3, all of the limits from as the f of x approaches to the same values as x approaches c from left and from the right. Okay, so in other words, for a limit L to exist, the limits from the left and from the right must exist and be equal to L. So meaning they must have the same values. Okay, so therefore, if they are not equal, then the limit does not exist. Just like number 4, example number 4. Okay, so these two, the limit from the left is 5, the limit from the right is 3. So therefore, the limit does not exist. Okay, so these limits are also referred to as a one-sided limits. One-sided because we only considered one side of C. C minus, one side, this is to the left of C. C plus is to the right of C. So that's why it's called one-sided limits. So let's review. So we have these examples, of course. This is the main result. Okay, and we have these two-sided limits that we have using the table So from the left, 2 minus, so this is from the left, the result is 7, and from the right, it's 7. Therefore, in general, meaning there's no plus or minus here, sa 2, then of course, since they are equal, so the limit here also is 7. Okay, in the other example, we have this. From the left is 2, from the right is 2. Therefore, the overall limit of the function is 2. As well as with this absolute value of x and this next example, negative 3. So the overall is negative 3. But in number 4, the limit from the left is 5. The limit from the right is 3. So therefore, they are not equal. Therefore, the limit does not exist. Okay, it does not exist. So far we've been using the table, okay, and choosing excess that is near to our constant c. It's either from the left or from the right. So we also have this. We may, if you want, you may graph the function and see the behavior of your limit of your x as x approaches the specific value. So consider this. This is one of our example. Y is equal to 1 plus 3x. So we have this graph, the straight line. Okay, now take note by just looking at this, since as x approaches 2, that's on our given example, as x approaches 2, so this is x. So 2 is here, so this is 2. Now look at what happens to our f of x. So it approaches this point at 7. So therefore, the limit of our function is 7. So the same with our previous answer. Okay, so here is 2. As x approaches 2, so as x approaches 2, as x approaches 2. Okay, so this one, so by just looking at the graph also approaches this point, dy equals 7, this point. Okay, now let's look at the second example. This is the graph. So as x approaches negative 1, so here is negative 1. So we have from the left and from the right. So the point is here. So the values of f of x approaches 2. Okay, so from the right and from the left, so it approaches 2. Yeah, next we have this example, absolute value of x from the left. So take note, it approaches here. From the right, it approaches here. So it's at y equals 0. So it approaches the 0 point or 0, 0. So the limit of the absolute value of x is at 0. Okay, example 3. So we have here as x approaches positive 1. So as x approaches 1, so this is positive 1. Okay, so what happens? As x approaches 1, so this is 1, so it approaches negative 3. Take note, it approaches negative 3. Okay, so therefore the limit of f of x is negative 3. So in example 4, look at this. As x approaches 4, so the first one from the left, it approaches 4. So here, the limit is 5. Okay, so ang f of x is 5. But on the other hand, if from the right, we have 3. Okay, so y equals 3. So therefore, we have no limit here. So the limit does not exist because the limits from the left and from the right are not equal. Okay, so in general, if we have the graph of a function such as below, so for example, we have this, determining limits can be done much faster and easier by inspection. Okay, so without using the table. So meaning if you can draw the graph, then of course it is easier. Okay, say for example, for instance, it can be seen from the graph of y equals fx. So this is the overall graph. So the limit of f of x as x approaches negative 2. So the negative 2 part is here. So we can say that Okay, so this is 1. So the limit of the function is 1. Okay, the y value is 1. So at this point. Okay, so just look at the y value. So limit of f of x as x approaches 0. So this one, so this is 0. This is the 0 point, the origin. So as x approaches 0, so we have this point here. Okay, although this is a whole, but still we are just observing, no, what happens to our f of x. So our f of x approaches the value of 3. So here it does not matter that f of 0 does not exist or undefined. Okay, always remember that what matters is the behavior of the function close to c equals 0 and not precisely at c equals 0. So that's it, no? What happens to our function as our x approaches 0? So clearly on this graph, our f of x approaches the 3. So y equals 3. So last, letter C, the limit thou does not exist, x equals 3, so this is 3. Okay, so it does not exist because we have this graph. So from the left, so as x approaches from the left, we have this point, which is 0. Okay, from the left, with 0. But from the right, if we look at from the right, so this is the graph, so therefore, the limit there is 4. So they are not equal. So from the right is 4, from the left is 0. 4, 0. So they are not equal. Therefore, the limit does not exist. Okay, now let's study the limit of a function at c versus the value of the function at c. So critical to the study of limits is understanding the value of the limit may be distinct from the value of the function as at x equals c. So let's study the limit of f of x as x approaches c and the exact value of f at c. So as seen in the previous examples, the limit may be evaluated at values not included in the domain of f. Okay, so we have an example there, the over x minus 1, I think example 3, that we can still find the limit even though 1 is is not part of the domain. Okay, thus it must be clear to you that the exclusion of a value from the domain of a function does not prohibit the evaluation of the limit of that function at the excluded value, provided of course that f is defined at points near c. Okay, because again in the limits we are just finding or observing what happens or what is the behavior of our function as x approaches, take note of the keyword, approaches to a specific value c. Okay, so near c, not equal to c. So let us again consider this example. So we have this, so from the left and from the right of 2. So we concluded that this limit is 7. Okay, in comparison, of course, if we substitute 2 to the given function here, so we have 3 times 2 is 6 plus 1 is 7. So both of these are equal. So notice the same holds for the next example. So we have these examples also. So the limit of this is 2 as x approaches -1. And if we substitute -1, okay, if we substitute -1 from this, so we have 2 because we have -1 squared, okay, squared plus 1. This is 1 plus 1. So this is 2. Okay, so they are the same. Of course, the absolute value of 0 is 0. Okay, so based on these 3 examples alone, we can say that maybe the limit of the function f of x is equal, as x approaches to c, may be equal to the f of c, or just evaluate the function by substituting your value of c. But this is not always the case. Okay, let us consider this new function here, piecewise function. So in contrast to the second example above, the entries are now unequal. Okay, so here in our previous example here at the top, they are equal, but here we have now a new function. So the limit of this one, of the absolute value of x, is 0. Okay, but of course, at x equals 0, okay, take note, because when we talk about this, we are talking about from the left and from the right of x. Okay, so meaning if we have this line, so our x here, or our c, is what? Equals 0. Okay, c is equal to 0. Of course, if our x is from the left, it approaches 0. If it's from the right, it approaches 0. Okay, approaches 0. That is why we have here. Now, at x equals 0, okay, now these values here, these are the values not equal to 0. Okay, these two values are not equal to 0. That is why we're using this. Okay, this one, the absolute value of x. But at x equals 0, which is this line, we are using the second function, so which is equal to 2. So here, f of 0 is equal to 2, right? So does this in any way affect the existence of a limit? No, not at all. This just shows that the limit of f of x and f of c may be distinct. Okay, so the limit of f of x as x approaches c and f of c may be distinct. So they might be or may be distinct. So it is not always the case that they are equal. Okay, furthermore, consider the third example. This is our third example on the lesson 1. So we have this piecewise function. So take note that the limit, no, does not exist. No, as we studied the left and right side of c, it does not exist. But of course, if we substitute 4, here, so we have 4 minus 4 is 0. Squared is 0 plus 3, so the result is 3. So again, these two are not equal. So once again, we see that the limit of f of x and f of c are not the same. So a review of the given graph. So we have these three examples in our previous slides. So limit of f of x is equal to 1 and f of negative 2 is equal to 1 based on this, because this is shaded. Okay, but here, limit of f of x, it approaches 3, right? Because when we say f of x, as x approaches a specific value, f of x also approaches to a specific value of y. Okay, so it approaches 3. But take note that if we substitute 0, but if we look at this graph at x equals 0, it is unshaded. Okay, unshaded. So meaning it is not part of the graph. So it does not exist, or it is undefined. Okay, the limit exists, but of course the f of 0 does not exist. Okay, these two are two different things, because again, this one is the behavior of f of x as x approaches a given value. This is at the exact value, f of 0. And last, letter C, the limit does not exist. Okay, because the first one is 0, the second one is 4, so these two are not equal, so it does not exist. So it's from the left and from the right. And of course, at f equals 3, okay, this is the shaded part. So it does not, also it does not exist, or it is undefined based on this graph. This is based on the, what do you call this one? The PDF of the uh, this one, the teaching guide for senior high school. But of course, based on this illustration, there is a point here. It is shaded. So therefore, f of 3 is equal to 2. Okay? So f of 3 exists and it's equal to 2. It is not undefined. Okay? So the point here is the limit of a function as x approaches infinity is not always equal to f at exactly c. So the two values are different. So I hope you've learned something about the introduction of limits, that when we talk about limits, we just study the behavior of our f of x as x approaches a specific value. Okay, so as x approaches a specific value, where will f of x approach? Okay, so thank you for listening.